My name is Jennifer Van Saders. I'm a graduate student at The Ohio State University, and I'm here to discuss a recent paper with Mark Pinsonneault in which we investigate a novel convective instability which is driven by non-equilibrium helium-3 burning in very low-mass stars. In stars like the Sun, the helium-3 is in equilibrium, but this is not necessarily the case for low-mass objects, where the rate of helium-3 production can outstrip the rate of its destruction. Furthermore, the reactions which burn helium-3, the primary of which at low temperatures is helium-3 plus helium-3, are relatively temperature sensitive, which means that these models can develop small convective cores, which are very analogous to the convective cores seen in much more massive stars burning via the C-No cycle. We can therefore have a scenario in which we have a small convective core, deep convective envelope, separated by a radiative buffer zone, and we're sensitive to the details of non-equilibrium helium-3 burning. We show a snapshot in time for a 0.36 solar mass stellar model. The left panel shows the temperature gradient as a function of radius. The dark dashed line represents the adiabatic temperature gradient, and the colored line the actual temperature gradient in the model. Regions in which the actual temperature gradient coincides with the adiabatic gradient are convection zones. We determine whether a region is unstable to convection via the Schwarzschild criterion, which states that when a radiative gradient necessary to transport the energy is greater than the adiabatic gradient, then the region is unstable to convection. On the right, we have the helium-3 mass fraction as a function of model age. As we step forward in time, we see that the helium-3 in the core steadily increases. This increase in helium leads to an increase in the luminosity from helium-3 burning reactions, which is accompanied by a few percent increases in the radius and total luminosity of the star. As the luminosity from the burning of helium-3 in the core increases, the boundary of the envelope and core convection zones move progressively closer together. When the two convection zones finally touch, the star becomes fully convective, diluting the helium-3 from the core throughout the star and quenching the helium-3 burning in the core. The model structure then returns to a configuration in which a convective core and convective envelope are separated by a radiative buffer zone. These cycles continue with decreasing amplitude and duration as the average helium-3 throughout the star is enriched over time, and eventually cease, resulting in a fully convective stellar model. Potentially one of the most interesting applications of this instability is in the context of cataclysmic variable systems, in which a donor star overflows its rho slope onto a white dwarf binary companion, and the orbital separation between the two objects gradually shrinks with time. One of the most striking features about the cataclysmic variable period distribution is an observed paucity of systems in a 2 to 3 hour period range. This period gap is generally explained by invoking some mechanism which severs the contact between the donor star and the white dwarf. Plotted here are the radii of several models subjected to constant mass loss rates. We see that as the stars pass into the mass range in which our instability operates, the radii respond in a complex manner. Such a radius change could be important for either severing contact with the primary or for the mass loss rates present in the system. Full evolutionary CV models are necessary to assess whether this instability is important for the evolution of CV systems. If you'd like a more detailed discussion of this convective instability, please see our paper, which is posted on the archive.